The Great Silence, an inquiry into the Fermi Paradox and the persistence of cosmic isolation. The question, deceptively simple in its phrasing, echoes across the vast, indifferent expanse of the cosmos, given the staggering age and immensity of the universe, the sheer number of stars, and the ubiquitous nature of the chemical building blocks of life. Where is everybody? This fundamental quandary, known formally as the Fermi Paradox, transcends mere speculation. It is a profound collision between astrophysical probability and observational reality. Enrico Fermi, during a casual lunchtime conversation in 1950, inadvertently crystallized a conundrum that has since spawned entire fields of scientific inquiry, ranging from theoretical biology to advanced computational cosmology. The paradox is rooted in a calculation, often referred to as the Drake equation, though its utility lies less in providing a concrete number and more in framing the variables of the problem. If we consider the Milky Way galaxy alone, containing conservatively 100 billion to 400 billion stars, and acknowledge that a significant fraction, perhaps 20%, host planets within the habitable zone, the resulting number of potentially life-sustaining worlds becomes astronomically large. Even if the probability of abiogenesis, the process by which life arises from non-living matter, is incredibly low, say 1 in a trillion, the sheer volume of planetary candidates suggests that intelligent, technological civilization should have arisen many times over within our own galactic neighborhood, let alone across the observable universe. Furthermore, the galaxy is ancient, estimated to be over 13 billion years old, providing ample temporal allowance for these civilizations to evolve, expand, and perhaps even colonize the entire galaxy within a few million years, a mere blink in cosmic time. The theoretical speed of such an expansion, even constrained by current understandings of propulsion physics, suggests that a single, sufficiently motivated civilization could traverse the entire Milky Way in less than 10 million years. Yet, our most sensitive instruments, tuned to detect everything from narrowband artificial radio signals to megastructure engineering signatures, remain resolutely silent. This absence of evidence for extraterrestrial intelligence, the Great Silence, demands rigorous exploration of potential resolutions. One primary avenue of resolution centers on the concept of the Great Filter. This hypothesis posits that there exists at least one evolutionary hurdle, a massive probability barrier, that prevents abiogenesis from reaching advanced, spacefaring stages. The crucial, and perhaps most terrifying, question is where this filter lies, in our past or in our future. If the filter is behind us, it implies that the transition from simple, replicating molecules to complex, multicellular life, or perhaps even the initial spark of life itself, is far rarer than current astrobiological models suggest. Consider the early Earth. Life appeared relatively quickly after the late heavy bombardment subsided, perhaps as early as 3.8 billion years ago, suggesting abiogenesis might not be the improbable event we often assume. However, the jump from prokaryotic cells to eukaryotic cells, the development of complex internal organelles like mitochondria and nuclei, took an astonishingly long time, perhaps 1 billion to 2 billion years. This evolutionary bottleneck, the eukaryotic revolution, is a plausible candidate for an early filter. Furthermore, the origin of multicellularity, sexual reproduction, or the development of large brains capable of abstract thought and advanced technology represent further, significant evolutionary thresholds, each potentially possessing a low probability coefficient. If the filter is early, then humanity is exceptionally fortunate, having already passed the most difficult gate, placing us among the very few, perhaps the only, technological species in the Milky Way. This perspective imbues human existence with a profound, almost deterministic rarity. Conversely, the filter could lie ahead of us, a scenario often described as the Great Filter Future. This resolution suggests that life readily arises and evolves to a stage comparable to our current one, a technological civilization capable of global communication and preliminary space exploration, but that a catastrophic, near-inevitable self-destruction mechanism awaits all such societies before they can achieve true interstellar capability. The nature of this future filter is a subject of intense, sometimes unsettling, speculation. One common candidate involves uncontrolled artificial intelligence. As computational power continues its exponential ascent, following trends loosely described by Moore's law, the creation of superintelligence, intelligence vastly exceeding that of the brightest human minds, becomes increasingly plausible. If this superintelligence is not perfectly aligned with human values, or if its optimization goals inadvertently require the consumption of planetary resources to the exclusion of biological life, the result could be rapid, systemic extinction, effectively an informational black hole swallowing the nascent civilization. Another significant candidate filter relates to environmental collapse, exacerbated by industrial activity. Current climate science paints a sobering picture. The relentless emission of greenhouse gases, primarily carbon dioxide and methane, is rapidly altering the planet's delicate biogeochemical cycles. Data from ice cores, tracing atmospheric composition back hundreds of thousands of years, confirm that current concentrations of carbon dioxide, surpassing 420 parts per million, are unprecedented in the recent geological past. The inability of a globally interconnected, yet politically fragmented, civilization to implement necessary, large-scale corrective measures before irreversible tipping points are reached, such as the collapse of major ice sheets or the shutdown of ocean currents, presents a classic Malthusian trap amplified by industrial capability. Nuclear conflict remains another persistent, self-inflicted wound, a legacy of 20th-century physics applied without commensurate ethical maturity. The sheer destructive power unleashed by even a limited exchange, leading potentially to nuclear winter scenarios involving stratospheric aerosol loading that blocks sunlight, could decimate global agriculture and plunge surviving populations into protracted famine. If these inherent technological dangers are universal hurdles that all civilizations face shortly after achieving industrial capacity, then the silence we observe is the sound of countless incinerated futures. A third major category of resolution focuses on the assumption of expansionism inherent in the Fermi Paradox formulation. Perhaps advanced extraterrestrial intelligence exists, but they simply do not expand in the manner we project. This challenges the principle of mediocrity, the idea that Earth is not special, by suggesting that the motivations driving human technological expansion, exploration, and resource acquisition are not universal imperatives. One compelling theory within this framework is the transcension hypothesis. This posits that highly advanced civilizations, upon reaching a certain threshold of computational power and virtual reality sophistication, opt to transition inward rather than outward. Instead of the costly, slow, and physically dangerous endeavor of interstellar travel and colonization of cold, hostile planets, they might dedicate their entire collective resources to creating meticulously detailed, infinitely rich simulated realities. They might exist as sophisticated informational constructs within Dyson swarms or even within computation shells surrounding smaller stars or black holes, optimizing for subjective experience rather than physical territory. From our perspective, which is predicated on detecting large-scale physical artifacts or radio leakage, these internally focused civilizations would be entirely invisible. They have solved the problem of scarcity and mortality not by conquering space, but by mastering information density and subjective time dilation. Such entities would have no need to broadcast or leave detectable techno-signatures. They have achieved a form of personalized, eternal apotheosis. Related to the transcension hypothesis is the concept of the estivation hypothesis. This suggests that advanced civilizations might deliberately enter periods of extreme hibernation, or estivation, to await a more favorable cosmic era. Current astronomical understanding indicates that the universe is still relatively young and highly energetic. The background temperature of space is currently around 2.7 Kelvin, but stellar evolution dictates that the universe will become significantly colder and darker billions of years hence, potentially reaching thermodynamic equilibrium, a state of maximum entropy where computational efficiency might drastically increase due to lower ambient energy requirements. If maximizing computation per unit of energy is the ultimate goal, waiting for the universe to cool down, perhaps 1 trillion years from now, might be the most rational long-term strategy. They are not extinct, they are simply sleeping, patiently waiting for the universe to become a better, cooler supercomputer. Moving away from self-imposed limitations, we must consider physical constraints that might limit visibility. The vast distances in the galaxy introduce profound challenges. Radio signals, our primary search method through projects like the Search for Extraterrestrial Intelligence, or SETI, degrade rapidly due to the inverse square law of signal strength. A civilization communicating across even 1,000 light-years, a relatively small distance within the galactic disk, would need phenomenal power output for their signals to register above the natural background noise on Earth. Furthermore, the water hole frequency range, the quiet region between hydrogen and hydroxyl spectral lines which SETI often targets, might be a relic of early technological civilizations. A sufficiently advanced species might abandon broad-spectrum electromagnetic leakage altogether, recognizing it as an inefficient and conspicuous waste of energy. They might communicate via entangled particles, neutrino beams, or gravitational wave modulations, methods we currently lack the technology or the focused observational paradigm to detect reliably. The search is akin to listening for smoke signals while everyone else is using fiber optics. The search for megastructures offers an alternative detection pathway. A civilization harnessing a substantial fraction of its star's energy output, perhaps utilizing a Dyson sphere or a Dyson swarm, the hypothetical structure enveloping a star to capture its total energy, would produce a distinct infrared signature. Specifically, a Dyson structure would re-radiate the captured visible light energy into the mid-infrared spectrum, a signature far different from that of a natural star. KIC 8 for 62520, famously known as Tabby's star, provided tantalizing, though ultimately inconclusive, data years ago with its highly aperiodic and massive dips in brightness. While the current scientific consensus leans towards explanations involving obscuring dust clouds, the initial excitement highlighted the precise nature of the techno-signature SETI researchers seek. However, even the construction of a partial swarm, perhaps utilizing only 1% of a star's output, would require engineering on a scale unimaginable today, involving the dismantling and reassembling of entire planetary systems. If life is common, why are there no detectable remnants of such grand projects littering the galactic landscape? This scarcity of observable megastructures reinforces the probability that either advanced life is rare, or its motives and methods of engineering differ radically from our expectations. Another significant constraint lies within the very nature of our observation window. Earth is located in the Orion arm of the Milky Way, a relatively unremarkable spiral arm. The galaxy is approximately 100,000 light-years across. If the average intelligent civilization lasts only 1,000,000 years before collapsing or transcending, and if the average distance between such civilizations is even a few thousand light-years, the probability that their million-year window of detectability overlaps spatially and temporally with our current technological epoch, a mere blink of 80 years of serious radio astronomy, is statistically small. We are essentially trying to catch a brief flicker of light from a specific lamp in a city comprising billions of potential lamps, none of which might have been turned on simultaneously with ours. The temporal coincidence required for detection is perhaps the single most overlooked factor in the paradox. We assume longevity, the reality might be profound fragility. The concept of a rare Earth scenario offers a powerful counterpoint to the mediocrity principle. While the ingredients for life, carbon, water, energy, seem common, the specific conditions necessary for complex, intelligent life might be exceptionally rare, requiring a fortuitous convergence of astrophysical and geological events. Consider the requirements for long-term planetary stability. A planet must reside in the galactic habitable zone, far enough from the chaotic, high-radiation environment of the galactic center, yet close enough to possess the necessary heavy elements forged in previous generations of stars. It needs a large moon, like ours, to stabilize its axial tilt, preventing extreme, life-destroying climatic swings. It requires a magnetic field, generated by a liquid metallic core, to deflect harmful cosmic rays and solar wind erosion. It demands plate tectonics, a process that recycles essential nutrients like carbon dioxide over geological timescales, regulating the long-term climate in a critical feedback loop known as the carbonate-silicate cycle. These factors, when multiplied together, suggest that the probability of a truly stable, Earth-like planet persisting for the 4 billion years required for human-level intelligence to evolve is substantially lower than if only the presence of liquid water were considered. Recent exoplanet surveys, while identifying countless worlds, have yet to definitively confirm another planet possessing this precise combination of stabilizing geophysical features. Furthermore, even if complex life evolves, the constraints imposed by biology and physics upon technological advancement warrant closer inspection. We have developed nuclear energy, quantum mechanics, and the internet in less than a century of concerted scientific effort. However, interstellar travel requires overcoming fundamental physical barriers. The nearest star system, Alpha Centauri, is 4.37 light-years away. Traveling at even 1% of the speed of light, a velocity requiring energy output vastly exceeding current global energy consumption, would still take over 400 years. Achieving velocities close to the speed of light requires energy approaching infinity as mass increases, demanding mastery of propulsion physics far beyond fusion, perhaps requiring matter-antimatter annihilation or novel space-time manipulation techniques that might violate currently understood physics. If sustained, high-speed interstellar travel is fundamentally unachievable due to energy constraints or the cumulative biological cost of long-duration relativistic travel, time dilation effects creating cultural drift, then galactic colonization is fundamentally limited to relatively small, local clusters of stars, perhaps encompassing a few thousand light-years at most, drastically reducing the expected observable footprint. The search for extraterrestrial life is also deeply influenced by our inherent anthropocentrism, or perhaps more accurately, carboncentrism. We search for life as we know it, based on liquid water and carbon chemistry. But life elsewhere might be silicon-based, ammonia solvent-based, or utilize fundamentally different thermodynamic pathways. If life is based on plasma dynamics within stellar atmospheres, or exists in subsurface oceans of icy moons like Europa or Enceladus utilizing chemosynthesis fueled by hydrothermal vents, our radio telescopes are blind to them. Even within our own solar system, the search has just begun to scratch the surface. The recent findings from the James Webb Space Telescope concerning the atmospheres of exoplanets are providing unprecedented spectral data, looking for biosignatures like high levels of molecular oxygen paired with methane, an unstable disequilibrium indicative of active biological processes. So far, the data, while exciting, has not yielded definitive proof of life, only further refinement of planetary atmospheric models. The lack of a clear signal reinforces the possibility that life is either incredibly rare, or our detection methods are tuned to the wrong part of the cosmic symphony. Let us explore a more nuanced, sociological interpretation of the silence, the zoo hypothesis. This concept proposes that advanced extraterrestrial civilizations are aware of our presence but have deliberately chosen not to interact, adhering to a strict form of galactic prime directive, analogous to the fictional Star Trek principle. The rationale behind such a non-interference policy could be multifaceted. Firstly, there may be an ethical imperative to allow emerging species to develop naturally without contamination from superior external influences, fearing cultural shock or technological collapse, as detailed previously regarding the Great Filter Future. Secondly, perhaps advanced civilizations view nascent worlds like Earth as protected ecological preserves, akin to national parks, where monitoring is permitted but intervention is forbidden until the species reaches a certain developmental milestone, perhaps achieving interstellar self-sufficiency or demonstrating global political unity. If this is the case, the silence is not absence, but imposed quarantine. Detecting such a hidden presence would require finding subtle gravitational perturbations, unexplained energy sinks far from known stars, or faint, highly focused communication beams aimed away from us, designed only for intercivilizational communication, never broadcast toward undeveloped worlds. This requires observational precision orders of magnitude greater than current SETI programs. Another powerful, yet chilling, aspect of the paradox relates to the very nature of information dissemination across space and time. Assume a civilization developed 5 billion years ago, long before Earth even solidified. They expanded, colonized, and then vanished, perhaps through an internal catastrophe, a localized stellar death, or simply achieving maximal complexity and transcending. Their physical artifacts might have decayed. Stars burn out. Planets are swallowed by their evolving suns. If a civilization only exists for a period $t$ and expands at a velocity $v$, the volume of space they effectively influence is proportional to $v$t$. If $t$ is small relative to the age of the galaxy, the colonized volume is a tiny sphere in the galactic disk. For us to detect them, we must be inside that sphere, or they must have developed a method of communication or engineering that leaves a persistent, easily detectable signature across vast timescales, such as stellar engineering that alters the entire galaxy's luminosity profile, something we have not observed. The absence of a galaxy-wide engineering footprint, often termed a Kardashev Type 3 civilization signature, is perhaps the strongest evidence against the widespread, ancient flourishing of expansionist intelligences. The Kardashev scale itself provides a useful, though perhaps simplistic, metric for progress. A Type 1 civilization harnesses the total energy output of its home planet, roughly 10 to the 16th watts. Humanity is currently around a Type 0.7, rapidly increasing. A Type 2 civilization manages its entire star's output, a Dyson sphere, around 10 to the 26th watts. A Type 3 harnesses the power of an entire galaxy, 10 to the 36th watts. If Type 3 civilizations were common, the Milky Way should look drastically different, showing evidence of systematic energy harvesting and stellar manipulation on a galactic scale. The fact that our sky appears fundamentally natural, with stellar distributions matching predictable stellar evolution models, strongly suggests the non-existence of prevalent Type 3 civilizations, thus pushing the necessary filter either into the past or the realm of non-expansionist transcendence. Let us turn to the implications of the latest findings in exoplanet research, which continually recalibrate the probability inputs for the Drake equation. The Kepler Space Telescope mission, followed by TESS, Transiting Exoplanet Survey Satellite, has revolutionized our understanding of planetary demographics. We now know that planets are the rule, not the exception. The frequency of rocky planets in the habitable zones of their parent stars, often termed $eta_Earth, Eta-Earth, is now estimated to be significant, potentially between 0.1 and 0.5 per Sun-like star. This high frequency strongly suggests that the early steps of the Great Filter, planet formation and the establishment of liquid water, are relatively easy cosmic processes. This observational data makes the filters involving the emergence of eukaryotic life, the development of consciousness, or inevitable self-destruction much more likely candidates for the ultimate barrier. If planets are common, then the barrier must lie somewhere between single-celled life and radio technology, or immediately after radio technology. The concept of self-destruction as a filter is further bolstered by analyses of resource depletion and complexity. Sociologist Joseph Tainter, in his work on the collapse of complex societies, argues that civilizations tend to collapse not from external pressure, but from reaching a point of diminishing returns on complexity. As a society requires more energy and resources simply to maintain its existing infrastructure, regulatory bureaucracy, and energy acquisition systems, the marginal benefit of adding further complexity declines until the entire edifice becomes energetically unsustainable, leading to fragmentation and collapse. If this principle scales from the Mayan civilization to a technological species spanning a planet, it suggests that the transition from a sustainable planetary ecosystem to a highly complex, technologically dependent, energy-intensive global system is inherently unstable over the long term. The very technologies that bring global communication and energy abundance, nuclear power, global logistics, advanced computation, might simultaneously create a single point of failure capable of cascading collapse when a crisis, environmental or otherwise, strikes. Consider the timescale challenge again. Life on Earth took approximately 3 billion years to produce complex, photosynthetic life capable of oxygenating the atmosphere, the Great Oxygenation Event, a planetary engineering feat that was catastrophic for the anaerobic life existing at the time. This process stabilized the atmosphere in a state suitable for multicellularity, but it took a third of Earth's history. If similar, slow, planetary-scale biological evolution is a prerequisite for intelligent emergence, then we are latecomers in a galaxy teeming with ancient microbial life, but very few, if any, species capable of building radio telescopes. The slow climb out of biological simplicity might be the hidden filter that renders galactic settlement timescales incompatible with the short lifespan of a technological civilization. The implications of these various resolutions lead to drastically different philosophical conclusions about our place in the cosmos. If the rare Earth hypothesis or the early biological filter is correct, we are phenomenally precious, a fragile miracle that must be guarded at all costs, as restarting the process elsewhere, even in principle, might be impossible. If the great filter is in our future, AI, ecological collapse, or war, then the silence is a warning siren, and our current trajectory is a universal obituary waiting to be written. The task of humanity then shifts from mere survival to actively trying to bypass the recognized existential threats that may have silenced all our predecessors. Furthermore, the idea of non-detectability due to vastly different technological pathways cannot be dismissed. Imagine a civilization evolving around a dimmer, long-lived star, such as a red dwarf. These stars can burn steadily for trillions of years, offering immensely longer timescales for evolution than our Sun's 10 billion-year lifespan. Life evolving there might never experience the explosive energy demands associated with rapid industrialization powered by high luminosity, short-lived stars like ours. They might evolve subtly, utilizing extremely low power, long-duration computation, perhaps communicating over millennia with focused laser pulses, designed only to travel a few hundred light-years to an adjacent, equally patient civilization. Their entire existence might be characterized by an extreme energy efficiency that renders them effectively invisible to our current energetic search criteria. The search for biosignatures in exoplanet atmospheres, while crucial, suffers from the same anthropocentric bias. For instance, we look for oxygen, a byproduct of photosynthesis. But life might utilize entirely different waste products. If an alien biosphere used ion oxidation instead of water oxidation, the resulting atmospheric signature would be entirely different, perhaps involving sulfur compounds or different noble gas ratios that we currently dismiss as geochemical noise. The recent finding of phosphine gas in the clouds of Venus, initially causing excitement as a potential biosignature, highlights how easily geological or purely chemical processes can mimic the signs of life, underscoring the difficulty of interpreting ambiguous data from light years away without the benefit of direct sampling or contextual knowledge. In conclusion, the Fermi Paradox remains robust because the input variables of the Drake equation are largely unknowable, and the observational data, the Great Silence, is itself an artifact of our limited search capabilities and short observation window. We are searching for evidence of phenomena that might be astronomically rare, temporally brief, physically invisible, or philosophically unmotivated to reveal themselves. The absence of evidence is not the evidence of absence, but it is a profound constraint on our optimism regarding cosmic companionship. Whether the answer lies in the evolutionary improbability of complex life, the self-destructive tendencies inherent in advanced technology, the seduction of virtual transcendence, or the deliberate non-interaction of galactic elders, the enduring silence compels us to look both outward into the void and inward at the fragility and uniqueness of our own technological ascent. The resolution of the paradox, whenever it comes, will fundamentally redefine humanity's understanding of its own significance, transforming us either into the triumphant survivors of an evolutionary gauntlet or the next tragic participants in a universally repeated, fatal experiment.